Hello. So we'll look at the cumulative deviations test. So all we have seen in the earlier cases, we have seen or we are focused on the signs test, and it was on the total number of positive signs as a whole. Right. Looking at from the complete perspective, the number of positive signs of the various size of age groups, whether it's undergraduation or overgraduation or undergraduation. Another way to really check out on a broader scale if there is overgraduation or undergraduation is this cumulative deviations test. So it checks out the overall bias. It does not check out the individual pluses or minuses. It's primarily considered with one figure of the overall level. The overall graduated rates are very high or low. Are they really reflecting the real world data? So what we generally do is we look at an overall figure under the assumption that the Z, so we compute the Z statistic here, which is nothing but observed deaths minus expected deaths so this is all divided by the standard deviation of the death. Now depending on what I'm using to model on the death, we have been discussing about the modeling of death. We're doing either through an assumption of through the poison, in which case the expected death will become the central exposed to risk multiplied by nu x plus half graduated rates. Probably this standard deviation, because in the Poisson distribution the mean and the variance are the same, so the standard deviation will become something like this, the same number. So I could have expected the expected death as standard deviation of the expected death, and this is expected to follow a normal distribution, which is a standard normal one. So the same logic if I'm using dx, that is modeled using a binomial distribution, then my mean would have been exposed to risk multiplied by qx graduated, or probably the standard deviation would have become the exposed to risk multiplied by qx multiplied by 1 minus qx. Now here, probably in this case, the qx is very, very small. So the probability of death within the next 1 year is very, very small. There is a possibility that this one will be much closer to 1, because this is very close to 0 and this will go closer to 1. So probably in the case of the binomial model also, the exposed to risk multiplied by qx could still give me the various standard deviation. So what we can do is we can compute the total the total expected death across all ages. I do this multiplication and addition. When I'm using a Poisson model in case of the expected death, I could have taken sigma center exposed to raise nu x plus half across all of them. I'm doing the summation and I'm taking out the z value. So probably depending on so here the 9 hypothesis is overall observed death are equivalent to or are more or less reflecting the expected death. So there isn't much statistical difference between the results. So if I'm looking at for a 95% confidence interval, any z value. If the z value goes below 1 minus 9.96 or it goes greater than 1.96, I will reject the null hypothesis. So the null hypothesis is the observed depth reflecting the expected depth. So the null hypothesis here is just the observed depth are reflecting the expected depth. So fitting the actual values to a large extent. So I'm rejecting this statement. If z is less than 1 minus 1.96 or greater than 1.96, so the null hypothesis can be rejected. So because I'm looking at both sides, so we consider these are the two-tiered kind of test. So very much lower. So if the z value is much less than 1.96, then observed deaths are much lesser than expected death. Expected death means expected deaths are the ones which are graduated. So the graduation rates are much higher. So the graduated rates are much higher. But if you see if the z is greater than 1.96, then the observed deaths are much higher than the expected death. That means the expected deaths are much lower, so the graduated rates are much lower on the overall basis. So that is how we execute the cumulative deviations test for various age ranges that are given. So I'm looking at the overall picture, like the overall within the various age group we have selected. What is the total number of observed death, and what is the total number of expected death? And based on that, we're trying to use, so what could very well happen in a large number scenario. Whenever we're talking about the expected death, the same value under the square root will add to the expected death itself. So if I'm assuming that the expected death is 100, then the standard deviation, I can take the square root of 100. Okay, so if I'm assuming the Poisson, where's the Poisson? So this is the Poisson. If I'm assuming the Poisson, or if I'm assuming the binomial also, assume that qx is very small value. Even this will boil down to a similar kind of calculation. Probably as a quick approximation, I can very well depend on taking the expected number of deaths square root as the standard deviation as the number of deaths. So just to summarize this, first we generate a hypothesis, the null hypothesis that the graduated rates are the true underlying mortality rates itself. And then we are carrying out this test, less than 1 minus 1.96 or greater than 1.96. We are rejecting the null hypothesis, and we are concluding that the overall graduated rates are either too high or too low. This is one more important test that we are performing on the graduated rates to check out for adherence to the data. So just to summarize until 9, whatever various tests we have looked at with respect to the adherence to the data, initially we started with the chi-square test, where we performed the standardized deviations test, and after that we have performed the chi-square test. From there we've identified that there are some drawbacks with the chi-square test. That's where we went with independent standardized deviations test. right? Deviations test. Then we also looked at for the science test. And now we're looking at the cumulative. We're looking at the cumulative deviations test. So one more important aspect we should look at is the grouping of the science test. Grouping. Why are we looking at this? When we talked about the chi-square test, one of the drawbacks we have observed is overall the z square might be less than the critical value, so I cannot reject the null hypothesis. But it may so happen that for certain age groups, for a stream of age groups, there's a positive graduation. For some of them, there's a negative graduation. Again, a series of positive, and again a series of negative. So some kind of overall, it cannot be over a highly positive or highly negative graduation, over graduation or under graduation kind of thing. But we are primarily looking at the clustering, or probably the clumping of the deviations. So we can say that at the younger age, my model is, or my rates are under graduated. After a certain overage, they're over graduated. So identifying that kind of patterns in the data can be very well executed in the grouping of science test. For this grouping of science test, we have to check out for how many positive science tests are there in the data, and how many negative science tests are there in the data. Okay, so just to look out for the same, assume that in your data there are n1 positives. There's some n1 positive science in the data, and n2 negative signs are there in the data. So we have one positive sign and two positive signs in the data. Now let's see what are the total number. So the total is n1 plus n2 kind of deviations that are there. So if I have to arrange, if I have to arrange n1 positive and n2 negative signs here, then let's say I have n1 plus n2 slots. I have to arrange n1 positives here. In how many ways can I do that? So I have n1 plus n2, so cn1 or n2 is correct. So these are the number of ways in which I can arrange n1 positive elements. I have n1 plus n2 locations. So the number of ways in which I can arrange n1 positives and n2 negatives in this is n1 plus n2c n1. So these are the total number of positives, but I have some restrictions. Now I'm looking at the groups. So assume that there are some n2 negative groups here, n2 negative values here. So now n2 negative values are already occupied, right? So if there are n2 negatives, obviously I have, let's say, 3 negatives, right? If I'm trying to fit in a positive group between the negatives, a group can be fitted here. A group can be fitted here, a group can be fitted here, a group can be fitted here. Now, out of these 3 negatives that are there, 4 groups can be fitted. So what I'm saying, if there are n2 negatives, n2 plus 1 kind of groups can be picked. So the slots that are available are n2 plus 1, right? Now I want t such groups to be fitted. If it's only one group, I have 4 slots which can be fitted in 4 ways. Okay, so I have t groups. I have n2 plus 1 which can be fitted into n plus 1 t. Okay, so once the negatives are fitted, there are n2 plus 1 positive slots in which different positive groups can be fitted. So they can be fitted in n2 plus 1 ct. Now within each one of them, right? Now I have t positive groups. Now the various elements that I have n1 positives with me. I have to fit into the t groups, which can be done by n minus 1c and then t minus 1. So obviously the probability of having exactly t groups, t positive groups, the probability of having, let's say we say the probability of exactly having t positive groups is coming out as n2 plus 1c t multiplied by n1 minus 1 ct minus 1. Then you divide this by n1 plus n2 cn1. So this is the number probability that I have exactly t groups of positive values. So now what I can do is test out with t is equal to 0, t equal to 1, depending on my values of n1 and n2. I'll check out for t is equal to 0 and t is equal to 1, and probably I will see in reality that in this case this is one positive group, this is another positive group. So there are two positive groups for me. So n1 is 5, 6, 7. Let's say n1 is so n1, these are supposed to be 5, 1, 2, 3, 4, 5, 6, 7. Look out for, so we have let's say 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 positives. And how many negatives do we have? 1, 2, 3, 4, 5. We have 6 negatives. So overall there are 14. Okay, so this gives us 14. So our test will go like, what is the probability that j is equal to 2? And this will be equal to 2 positive groups. So n2 plus 1. So n2 plus 1 is what? What's our n2 plus 1? 7c2 multiplied by n minus 1. 7t minus 1. T is 2 groups. 7c1 divided by n1 plus n2. 14c8. Now I check out what is the probability for this. Also check out what is the probability of j is equal to 1 and j is equal to 0. I add up these 3 probabilities. if this total is coming out to be less than 2.5%, if this total is coming out to be less than 2.5%, I will reject the null hypothesis, which says there is not much of a concentration in the deviations, concentration in the division, or like maybe over graduation or under graduations in patches. There is a definite over graduation or under graduation in patches for different age groups. Either they're over graduated heavily or undergraduated heavily. So you can take up the numericals to work out that. So the number of positive deviation is less. We also have a critical table. In the actual table, you can get the critical table. We can get the critical values in the actual table. If you see that the number of groups of positive deviation is less than the critical value from that table, I can reject the null hypothesis. Otherwise, I cannot reject the null, and I have to say that there is not much of concentration of deviations across the various age groups. So we cannot conclude that there is excessive grouping of signs. But if I'm rejecting the null, I have to conclude that the groupings of signs is pretty much the same. So that is one more test, especially to see overall they may not be positives or negatives, but there are some groups of positives and some negatives. Even that kind of concentration also tells us that at certain age groups the graduated model is undergraduated, whereas at certain other groups it is overgraduated kind of thing. Okay, and probably the same can go as part of a normality approximation also, right? One is through this direct method. The second, I can even consider, if the groups are very large, I can consider that the number of positive deviations follow a normal distribution. You can take n1, n2 plus 1 divided by n1 plus n2 for the mean for the normal distribution, n1 n2 squared divided by n1 plus n2 cubed. This is the number of deviations following normal distribution with mean this and variance equal to this. So probably I can find out the actual number of, so this will give me the expected number of positive deviations and actual positive. So I'll take the z value is equal to actual positive deviation, positive groups, actual positive groups minus expected positive groups minus the expected positive groups. So the expected the n1 plus n2 and the standard deviation of the number of positive groups into all squared by n1 plus n2 cubed. So this is what can be very well performed for less than 1.96 or greater than 1.96. So plus 1.96 we can well restrict to this, but generally what is advised, if n1 or n2 is greater than 25, then only it's better to use this kind of mechanism of approximation. Let's say you're trying to cover 50 age groups and 30 of them are showing positives and 20 are showing negative. Then such kind of data, if it's there when I'm observing across the kind of pick a large set of age groups, and in that case probably it is advised it is advised to take the normal approximation kind of method. So one more test in this one more test regarding the same of deviations in a particular age group, right? Probably just like this accumulation of science tests, or just like this grouping of science tests, one more test which can address this situation is the serial correlation test. Also, serial correlation test, another way of addressing the same problem. Serial correlation test. Here, all I'm looking for the serial correlation test is I take one time period lag. So if I have the data, this is the data, I'm taking, let's say, Z1 to Z30, age group, let's say 21 to 50. So I'm taking a serial correlation. If I want a serial correlation, all I would take is I will take a correlation with respect to Z1 to Z29. So here there's a Z2. So logically I'm trying to do a correlation between Z2 to Z30 versus Z1 to Z29. So this is the correlation I'm trying to do here, right? With a lag. So here I'm saying I'm doing correlation with lag 1. So if I'm doing the correlation with lag 1, actually what has happened, the general formula for correlation is covariance divided by standard deviations of both of them. So standard deviation of A, standard deviation of B. So here what we're trying to do is, so covariance comes out as X bar. Okay, so what we're saying is Zi minus Z bar, Zi plus 1 into Z bar. So Zi minus Z bar is probably Z1 to Z29. Zi plus 1 minus Z bar is Z2 to Z30. So across all of them, so I'm getting a summation here from I is equal to 1 to 29. Though I have 30 elements, I'm only taking up to 29. Okay, so we'll say this would be M minus 1. So these numbers, I require the covariance. I require to divide this by M minus divided by standard deviation of A and B. Actually, both of them are from the same data, so the standard deviation will still remain the same. So I'll take the standard deviation Zi minus Z bar squared, which is nothing but the variance. So this is what I take, especially for the computation for serial correlation. And the serial correlation, I will check out for the serial correlation under the normal distribution assumption. So this is coming out as R. So I'll do R into R squared of M, number of deviation. I assume this is following a normal distribution with mean 0 and variance 1. So based on the normal distribution values, I can very well check out, but the default null hypothesis R is equal to 0, which means there is no serial correlation present in the data. Means they are independent. Whatever the deviations that are coming out, the positives or the negative, they are completely independent. But if my z is actual correlation, because I'm saying R square root is following a normal distribution, so I will take the R square root of m, right, minus whatever the expected value is, which is 0, because R squared root of m is directly following a standard normal distribution. So I can use the standard normal distribution corresponding to that. See if the R square root of m is, if it's coming out less than 1.96 or greater than plus 1.96, I will reject the null hypothesis and say that there is a definite serial correlation in the data. Otherwise, I don't have the sufficient evidence to reject the null hypothesis. But here I'm more interested only for the positive correlation. So I'm only interested in the positive correlation. I'm not bothered about the negatives. So I'm looking at as a one-tailed test. So I will take 1 period lag value of all the individual standardized deviations that I'm getting. I can compute R1 using this particular formula. Okay, and then I'll take R1 multiplied by square root of m, right? I can compute the correlation between this and this. So whatever the R I'm getting, I multiply by the square root of m. Then I will test with the assumption of normal distribution of 0 to 1. So if at all I'm seeing that the number is greater than, because it's a one-tailed test, I'm looking at the 5% itself. So if my calculated z value, which is R squared of m, is greater than 1.65, then I will reject the null hypothesis and say that serial correlation is present in the data. Otherwise, I don't have a sufficient evidence to reject the null hypothesis. Then I cannot say that any kind of significant positive correlation in the data are coming up. So just to summarize up, we are talking about 6 major tests. Starting off with the chi-square test. To address the first problem of the chi-square test, which is overall some small deviations, large number of small deviations are offsetting the small deviations. To address that aspect, we took up an independent standardized deviations test. To address the second problem of the chi-square test, all positives and all negatives kind of undergraduated or overgraduated, we have taken up the science test as well as the cumulative deviations test. And to address the third problem associated with the graduation of the chi-square test, for some age groups, there could be over graduation, there could be some under graduation, or in a serial manner. So we have tried the groupings. We have tried using the groupings of science test, as well as the serial correlation. So these are the tests which are available to check out if the graduated rates are adhering to the actual values or not. But on the other side, to test out the smoothness, we had only one mechanism. So for the smoothness, we had the third difference of the graduated rates. So we're looking at the third difference should be much smaller in comparison with the graduated rate, and they should be increasing gradually with respect to age, right? So regarding all these things, you can take up some kind of numericals to take up the understanding of all these various aspects. But from a conceptual standpoint, I hope that the purpose of doing this various statistical tests for the testing out for the graduated rates is clear. And you can very well apply these various aspects for various business scenarios, right? So we'll come to the end. I wish you all the best in your studies and for the exam. If you have any other questions, you can drop me a text either on WhatsApp or an email. Thank you so much.